Hi, everyone. Welcome back to another Math 104 lecture. So it's been a little bit since we have picked up on these. So let's just refresh ourselves. The last lecture that we had was if you're following along in the textbook, it was chapter 2.3, which is lines. Today, what we're going to be looking at is the next section, so chapter 2.4, and this is going to be focusing on functions. In advance, I know that I said I'm not huge on definitions. This one is laden with quite a bit of definitions, so just bear with me. I'll try to make it as painless as possible, and then we'll get to the computational things soon enough. So, what is a function? Let's start there. So, a function, and we're writing in red for no reason. Let's try again. So, a function, which is what we're looking at. This is going to be something that maps any element, or every element, I should say, every single element from one set to exactly one particular element of another set. So let's, for example, say I have a set over here, and we'll call this A, B, and it has the elements A, B, C, and D, right? And we'll call this set A, and then over here in set B, we'll have, some other things, right? We'll say, E, F, G, and H, right? And the idea of a function is that you're going to take your things, and they don't always have to correspond, directly across, but you're going to take your things, and the elements from set A are going to correspond to some particular element over in set B. So that's the idea here. It's just, corresponding elements. And if you think of, when we were graphing things, what an ordered pair is, it's essentially that, right? You had some sort of input, and your input corresponded to some sort of output. Regardless what your equation was that you were graphing, you had something that you were putting in, you did your computations, adding, subtracting, multiplying, whatever the case was for that particular equation, and then your dependent variable had some sort of output. That was your output, right? If we're talking about an ordered pair x comma y, x was generally your input, that's your independent variable, y is your output, y was your dependent variable. So this is going to be the same exact idea. It's just a little bit handier of a notation that we can describe input and output. Okay, so the way that we regard functions, we talk about functions as such. And the way that you read this is f of x or f at x. Please note that this does not mean f multiplied with x, okay? F is not a variable here. F is saying that there is a function, and it's a function of x. X is your independent variable, which means that when you're plugging whatever your independent variable is, whatever the value is, you're plugging it into your function f, and then it's going to spit out some kind of output. Again, think about it in the way that when we were talking about equations, you had your independent variable, again, generally it was x, and then it spit out some sort of output, which is what y was equal to. It's just in this case, instead of using y, we're using the function notation, f of x, okay? So let's think about some facts that are specific to functions. So specific to functions, there's four things that we should really know. The first thing is domain, okay? So domain, and we talked about domain quite a bit, going into this chapter. We've talked about it, going even way back, to just the earliest chapters that we, first started with. But regarding functions, the domain of a function f is all the possible values of your input set. Okay, so all the possible values. And I'm going to call my input set capital X, just so, it remains consistent with the way that we've learned equations where, lowercase x was your input variable. So all the possible values of input set capital X. Okay, so again, your domain, this is just saying that your domain of a function is going to be every single element that that you could, in theory, plug into the function. So if the only two numbers that you're allowed to plug into your function are 0 and 2, for example, then your domain is just 0 and 2. And that's it. It's pretty simple for domain is concerned. Then we have range, which is a pretty common term. Hopefully you guys have heard of range before. The range of a function f is going to be all the elements of set y. So again, set y, I'm going to call that my output set. And again, I'm also going to call it capital Y here because we've learned that in general, our dependent variable is our output. So it's going to be all the elements of our output set y that have been assigned to an element in set x. So I'll write that out again. So all the possible elements in output set y such that they've been assigned to some element from set x. And I'm just going to abbreviate such that they've been assigned to an element from set x. Now, don't get caught up or hung up on the definitions. Again, I'm writing these out just for posterity, so that way you have these in your notes, so that, you know, hopefully it makes more sense. Right now, this, I'm sure, just feels like a bunch of words coming at you that really make not a whole lot of sense, okay? But just write it down, have it for yourself, and that way when we get to some examples, you can come back to these definitions and be like, okay, this is what he actually meant, okay? So those are the first two things that you should know regarding functions. The second two things are really more specific about functions as far as how they operate and how we define them, okay? So the next, and these two are far more important. They're good things to keep in mind. Domain, you should have already had a handle on. Range, once you see a couple examples, it's not going to be too different from domain, so you'll get an idea of it. But these next two things, these next two ideas, are particular to functions where we haven't seen these ideas before, okay? So the next thing that you should know about functions is that one singular element of set y, so one output, essentially, can be mapped to multiple elements of your input, okay? So what do I mean by that? So that essentially says we could have 0, 3, and we could also have 1, 3 in our graph, okay? So if we were graphing some function, and notice, again, our inputs are going to be the first things. Our inputs are our x, right? Notice how this is the same element, right? I said one single element of your output can be mapped to multiple elements from your input. So notice, again, if we're drawing this in the same way that we had way up here for, you know, the visual of the sets, right? Essentially what this is saying is we could have 0 and 1, and we could have 3 over here and, you know, some other outputs, right? And 0 could map to 3, 1 could map to 3, and that's totally okay. That's absolutely allowed. You can have different inputs map to the same output, okay? However, one singular, and this is this fourth item that we need to discuss, one singular element of your input cannot be mapped to multiple elements of your output, okay? So I'm going to put a check mark here because this is okay. But now if we come over here, and I'm just going to put a dotted line here just so that was a horrible dotted line. Let's try that again. I'm going to put a dotted line here just so we understand that this is the other case. One singular element of your input cannot be mapped to multiple elements of your output. So what this says is, say we had the ordered pair, I don't know, 1, 2, and then also we had the other ordered pair. If I could scroll, that'd be great. There we go. 1, 4. This is not a function. This would not be allowed. Why would this not be allowed? Well, this is again saying you have your input, and your input again, let's say we have 1 and some other inputs that don't necessarily matter, right? But again, 1 is going to be the one that we're focusing on here, right? And for our output, we have 2, 4, and whatever the other outputs are, doesn't matter, right? What this is saying is you can't have one input going to 2 different outputs. Notice how this is different, right, from this example over here. We have 2 inputs going to 1 output. Over here, we have 1 input going to 2 outputs. This is not acceptable. We can't define, this would not be a function, whereas this would be still considered a function. This would not break the rules of having a function. Okay. Again, this might seem like jargon at first, but when we get to real examples, it'll start to make more sense. All you really have to consider is just that you can't have a single element from your inputs going to 2 different answers. Okay, if that happens, it's not a function. Okay, so we happen to write, I'm going to clear this off here. We happen to write particular values of input and output in the form f of a is equal to b. Okay, where a is going to be your input and b is going to be your output after, whatever your input, in this case a, was applied to your particular function, right? So for example, if we had f of 3 is equal to 7, this implies that after you plugged in 3 to whatever your function was, the output of that would be 7, okay? And this is really handy for notation because this directly corresponds to this notation for ordered pairs. Again, your input is 3 and your output is 7, right? And they can go back and forth. You can, if you have this ordered pair notation first, you can go backwards as long as it actually is a function, because we'll see in a second that not everything can be a function. But you can go from the ordered pair to this function notation saying that, oh yeah, as long as I plug 3 into my function, I'm going to get 7 back. So these are interchangeable. Okay. Again, they're only interchangeable if whatever you're plugging into actually is a function, and we'll show cases where things are a function and things aren't. Okay. All right. So what happens if things aren't a function? Well, we have another definition called relations. Okay. So a relation. A relation is just really simply any set of ordered pairs. It doesn't have to have any specific rules. So any set of ordered pairs is considered a relation, okay? The first component of each pair, so the first component of every ordered pair makes up your domain of the relation, and that should make sense, right? That's your input. Again, what I'm talking about when I say the first component, I'm talking about this piece right here, your X. So that makes up your domain. So when you have a set of these ordered pairs, and I'll just write a couple down, just so we're all following along. 0, 1, 2. Call that x0. So your x's make up your domain, and your different y's make up your range of the relation. Okay, so again, you have two different sets. Same thing with functions, and honestly, the same thing that we've been talking about with equations beforehand. A relation is a function only if each element of the domain corresponds to exactly one element in the range. In other words, where your x value is not repeated. Again, the example that we just did, where we had 1, 2 and 1, 4, and we said that, oh yeah, this is not a function, right? Notice the reason that it's not a function is because your x is repeated. If your x is repeated, that's a telltale sign that this is only a relation and that this relation is not a function, okay? Okay, so let's get to an actual example here. So let's say we're given the set, given the set R, and R is made up of the following ordered pairs. So R is made up of 2, 1, negative 2, 1, and 3, 2. Okay, so this is our set, okay? And what we have to do is I want to determine the domain, the range of this, and I also want to figure out whether or not this is a function, okay? So let's think about it. Domain, like we just talked about, the domain of a relation is just going to be all of your initial inputs, right? All of your inputs that are going in to each ordered pair. So when we think about inputs, again, that's generally your x's, right? So that's going to be this, this, and this, right? So we could say the domain of R is going to be just essentially the list of the first components. So, and I'm going to call that set X, set capital X, because again, I'm just trying to remain consistent since we generally call that the X component. I'm just going to call this, capital X for my set. Okay, so my domain is 2, negative 2, and 3, right? Again, 2, negative 2, and 3. Those are all of my inputs. Okay, and over here, I'll also write domain just so we're all following along. Okay, now also, I want to find the range of this, right? So finding the range of this, well, the range is only going to be the outputs, right? So the range is going to be all of the y values, all of the things that are going to be output from my ordered pairs. So that's going to be this, this, and this, right? The 1, and the 2. So let's go ahead and write those down. And remember, when we're writing down sets, we don't have to repeat numbers, right? If we see that something repeats, we only have to write it once when we're writing the set, right? So we're going to have our range here. And again, I'm going to call this set capital Y because, again, as we see, we're talking about the Y components of every ordered pair. So we end up with just the set of 1 and 2, right? Notice that 1 is being repeated in the first and the second ordered pairs. So we just need to write it. We just need to write 1 once. Okay. And now the last question is we have to determine whether or not this relation is a function. Okay. Now remember, the only constraint, the only difference between a relation and a function is whether or not your x is repeating. If your domain repeats, it's not a function, right? So we look at our x's for all the ordered pairs. We say, okay, we have a 2 here, we have a -2 here, and we have a 3 here. And since those are the only 3 points in our relation, well, we see that x does not repeat, right? We have a 2, a -2, and a 3. These are all distinct different numbers. It does not repeat. So yes, this is in fact a function. So I would just write R is a function. Okay? And it's that easy. Again, the idea here is just that your y's can repeat. And in fact, we do see that our y repeats here. We have a 1 and a 1 here, but that's okay. If your output repeats, that's no problem. As we saw, remember, this was okay, right? When we had our 2 sets, we had our 2 elements and 1 element over here. This was totally fine. And we see over here, that's what's happening, right? We have 2 and we have -2 corresponding both to 1, right? So I could rewrite this essentially as 2 and -2. And we have 1 over here, and notice that they're both corresponding to that, and that's totally fine, right? What we couldn't have happened was if we had a situation where one input was going to 2 different answers. So what we can't have is, again, if we have A, and over here in our output we have B and C, and A would be going to both B and C. That would not be acceptable. But seeing as how that is not the case, we see here that our x is never repeating in our ordered pairs. This is absolutely a function. So we're okay with this. Okay. All right. Let's go ahead and clear that off and we'll keep on moving here. Okay. So let's talk about functions and how they correspond with equations, because up until this chapter, we've really just dealt primarily with equations. But again, keep in mind that when we talked about equations, especially within the most recent chapters, we talked about dependent variables and independent variables, right? We talked about how if we're plugging something in, we're doing operations to whatever we plugged in, and then once we get that, we then have an answer for our dependent variable. Our independent is the things that we're plugging in, dependent is the answer that gets spat out, right? So our general idea here when we want to convert an equation to a function is we want to solve for the dependent variable, okay? And then once we've solved for the dependent variable, we will then replace it with f of whatever our independent variable is. Again, I know that sounds like a lot of jargon, so let's look at an example here. So let's say we have y plus 3 is equal to x squared. And again, the way that we've learned this up until now is that your dependent variable is y, right? We generally solve for y. X has always been our independent variable. X has been the things that we're plugging into. And then we do operations on x, and then we get an answer for y, right? So y is very much dependent on whatever we plug into x. So we're going to solve for y because, again, we're trying to solve for our dependent variable. So what we're going to do is we're going to subtract 3 from both sides, which means now we have x squared minus 3. So y is equal to x squared minus 3. And now what we can do is we can just replace y, which is our dependent variable, with f of x. We can put this into function notation. So we can just say, I'm going to put an arrow here. You don't necessarily need to put an arrow here, but I am just showing we are just replacing y with f of x, and we just keep the other side the same. And now this is functional notation. We say the function of x is equal to x squared minus 3. This is our function f. Okay. And now this is really handy for defining particular values. It's really great for getting particular answers and like particular ordered points. Let's say, for example, I wanted to, based off of this that I have right here, I want to see what f of x would be if x is equal to 3. So if x is equal to 3, find f of x. Okay, well, that's really easy, right? We know that this right here tells us x equals 3. X is 3. So wherever there's an x, we plug 3 in, right? So we say that f at 3, because again, we're plugging in 3 for x. So our function f at 3 is equal to 3 squared minus 3. We know 3 squared is going to be 9, so 9 minus 3, and 9 minus 3 is 6. So we just say that f of 3 is equal to 6. And once again, this is really great for us because we can transfer this into an ordered pair, right? Our input, this tells us our input was 3 and our output was 6. We now have an ordered pair directly coming from our functional notation, okay? So again, this would read, our final answer here would read as the function f at 3 is equal to 6, and it maps the value 3 from one set, which again, our starting set is going to be the domain, to the value 6, which is the other set, the range. So we're going from one set to the other set, and if we're, again, showing the visual of the sets, where this is my input, and we call this capital X, and this is my output, and we call this, oops, there we go. We call this capital Y. I don't know what the other inputs and outputs are, but we know that we're plugging 3 in, and we know that we have 6 over here, and 3 directly corresponds to 6. And that's, again, just the visual representation of what's actually going on here. We have our domain, which I'm just going to put a D over here. We have our range. So 3 from our domain maps to 6 to our range. And it's just that, okay? So again, we have to consider if all equations are functions. And the answer is no, right? The answer is absolutely not, in fact. Most equations, in fact, are not going to be functions. Let's look at an example here where we can plainly see that this is not the case. So consider a circle. We talked about circles a bit before, and the unit circle has come up quite at least a little bit. We've talked about this equation here, x squared plus y squared is equal to 1. This is the unit circle, right? 1, remember, this is 1 squared, and 1 squared is basically your radius squared, which means your radius is equal to 1, right? So this is, again, what we consider our unit circle. And let me go ahead and actually roughly graph this. I'm not going to make it too big of a deal with it, but let's call this 1. So just, pretend that this is a perfect circle. It's not horrible, could be better, but not bad. So again, we have our unit circle here, right? Okay, so the idea of this is notice how if we're talking about our inputs from, our input, our domain, our input is going from, well, this is -1, right? So our input is going on the x-axis from -1 to 1. And we should solve this x squared plus y squared is equal to 1 to be in the form of a dependent and an independent variable. So what I'm going to do is I'm going to solve for y, because again, solving for y, then we have it in the form of, we plug something in for our x, and y is our dependent variable. So solving for y, that means we have y squared is equal to 1 minus x squared, and y is equal to plus or minus, remember, we're taking the square root of both sides, so plus or minus 1 minus x squared. And the reason that I'm taking the square root is because I have y squared, right? So to undo the square root, we take the square, or I'm sorry, to undo the square, we take care of the square root on both sides. So now we get y is equal to plus or minus 1 minus x squared. Now notice that we have a problem here. Why do we have a problem? Well, our problem is that we plug in some number for x, right? We plug in something for x, and then when we plug something in for x, we're actually going to get two different answers. We're going to get the positive and the negative answer. So when we're talking about input and output, we're plugging one thing in for x, but we're going to get plus y, and we're also going to get minus y, right? We're going to get two different answers here. And that means that this is in fact not a function, right? This is not acceptable. We can't have one input mapping to two different answers. That's not okay. Another way to think about this is notice how I can take any x in the circle, right? So say I'm talking about just right here, right? So this point right here, and this point has some particular x. It's less than 1, but I don't necessarily care what it is. You can call it 2/3 if you want, whatever, we'll just say x is equal to 2/3 here, right? Well, notice that our y value for x is equal to 2/3 is at this point here, but it's also up here at this point. X is 2/3, like x is equal to 2/3, maps to two different points on the circle. And hence we have two different y values. So we see here that this is not a function. A circle is not a function, okay? But remember, we talked a little bit about semicircles, right? And semicircles are where you essentially just break up the positive and negative square roots into just the positive square root or just the negative square root, right? If we're talking about the top half of a circle, so the top semicircle, that's just going to be the positive version of 1 minus x squared, right? And again, roughly sketching this, we're essentially just talking about this, where this is 1 and this is -1, right? And this is totally okay. And the reason that this is a function is because notice now when we plug something in for x, we're only going to get one particular answer back, right? We plug something into x, we do our operations, and we no longer have the plus and the minus. We're only talking about just the positive version. So a semicircle is in fact a function. And if we talk about the other one, so y is equal to the negative version of 1 minus x squared, and that's just going to be the bottom semicircle, as we learned. So that's essentially that, right? Again, from -1 to 1. Well, this is totally okay as well, because notice that any x that I pick, so any x that I pick right over here, I'm just drawing a dotted line, I'm only going to have one output that corresponds to it. I no longer have this top output right here as well that's causing me some sort of interference. So I'm only going to have one single value of x resulting in one single value of y. And that's absolutely acceptable. And by the definition of functions, these are okay. All right. So hopefully that makes sense as far as showing you guys that not every equation is going to be a function, only particular ones that satisfy the definition of functions, okay? All right, so let's do some evaluations of functions. Now we're beyond the point of definitions, we can actually get to some actual math, okay? So to evaluate a function, all you're gonna do is you're gonna plug in your input into the function. And then you plug and chug, you do your operations, and whatever it comes out to be, it comes out to be, and then you're done, okay? So let's look at an example here. Let g be the function defined by, I'm going to just shorthand this, but let g be the function defined by the equation y is equal to -2x squared plus 5x. And again, just that's a 2. So -2x squared plus 5x. I want to find g of 1 and also g of x plus h. Okay? So what I'm doing is notice I'm finding two different points, right? If we're talking about functions, when we have a function, we plug our input in. So we have an input here of 1, and we have an input over here of x plus h. Okay, we're going to have two different answers depending on what we're plugging in. So we're starting with our equation, y is equal to -2x squared plus 5x. Okay, now what did we learn just a couple minutes ago? Well, we learned that now that it's in, dependent and independent form, right? We have our independent variable x and our dependent variable y. Y is already solved for, it's already by itself, right? So we have it in independent and dependent form. We can then just directly substitute our y for g of x. So we can just say, okay, well, this is really g of x is equal to -2x squared plus 5x. And now what do we have to find? We have to find g of 1, and we have to find g of x plus h. So these are going to be two different equations, two different answers that we're going to have. So let's do g of 1 first. G of 1 means we're plugging 1 in wherever there's an x, right? This 1 implies that this is our input. So wherever we have an x, we're plugging in a 1, and we say, okay, g of 1 is equal to negative 2 times 1 squared plus 5 times 1. Okay, we go ahead and do some simplifications. So 1 squared is still just 1, and negative 2 times 1 is still just negative 2. So we have negative 2 over here. 5 times the positive 1 is still just positive 5. So negative 2 plus 5, and that should give us 3. Right? So we can then say g of 1 is equal to 3. And if we wanted to go the extra step and say that this is an ordered pair, that's not part of the directions, but I'm just expanding here. If we wanted to get the ordered pair here, the ordered pair is 1, 3, right? Our input is 1, so our input is 1, and our output is 3. So our x would be 1, our y would be 3, and that's how you could think about functions. Again, the g of 1 is equal to 3 is just saying that when you're looking at your function g and you're plugging in your input of 1, your output will be 3. Okay, so g of 1 and g of 1. Okay. So next up, what we have to do is we have to find the next input. So our next input was g of x plus h. Okay. Don't get confused here. I know there's more going on in this one than there was in just g of 1. But remember, whatever is inside your parentheses is your entire input, okay? So wherever there is an x, so there's an x here and there's an x here, right? You're going to be plugging in your input, which is x plus h, okay? So your input, again, is x plus h, and you're plugging that in wherever there is an x, wherever you can plug it in. Okay, so we write, okay, g of x plus h is going to be negative 2 times x plus h. Remember, there used to be an x here. It just used to be an x, but we're plugging in our total input, right? Our total input is x plus h. So it's now negative 2 times x plus h squared plus 5 times x plus h. Again, notice here our input was only a 1, right? So it was negative 2 times 1 squared. Well, here it's negative 2 times x plus h squared. That is what we're trying to find, right? That's our input right here. So we're trying to find this, and now all we have to do is just simplify. So let's just simplify this. So simplifying, well, I am going to expand that x plus h squared, and you can either do that with foiling or you could do it with our blueprint, right? Remember, I'm just going to write this off to the side over here in green. Our blueprint, as we all know by now, a plus b squared is equal to a squared plus 2ab plus b squared. Well, our things, our variables, are just x plus h, right? So really all you have to do is just replace a and b with x plus h, and you get the exact same thing, right? So x plus h squared is x squared plus 2xh plus h squared. And great, we've now expanded that. And now we just have the negative 2 on the outside. So negative 2 times x squared plus 2xh plus h squared. And once again, you can accomplish that exact thing, this piece that I just, got using the blueprint. You can foil it and get the exact same thing. So if you need to foil it, by all means, do that. Okay, and over here, I'm just going to expand and distribute the 5 to the x plus h. So we get 5x plus 5h. We're almost done. Let's go ahead and distribute the negative 2, and then we'll condense terms wherever possible. So over here, we have negative 2x squared minus 4xh, right? The negative 2 times the middle piece, positive 2xh, gives me a negative 4xh, and then minus 2h squared plus 5x plus 5h. And as it turns out, there is actually no simplifications that we can do. This is in terms of x, this is in terms of h, this is in terms of h squared, this is x squared, and this is xh. So there's nothing that's going to combine. So as a result, we can just leave it in this form right here, and that's going to be your final answer. Okay? The important thing, I know that this looks really messy, and it might not look like your final answer, but the important thing is you notice that we're plugging in some new input, right? Our new input is x plus h, and wherever there was an x in our original function, we are plugging in that input. And then you're just doing normal operations to get there, okay? So I want you guys to try your first classwork assignment. The classwork assignment is using this exact same function of g, I want you guys to find g of x minus h. So this was what we just did was g of x plus h. I want you to find g of x minus h and see if you can get the correct answer. Okay, so give it a shot, see what you come up with. Okay, so let's give it a shot together. So we're trying to find g of x minus h using, again, the same equation that g is defined by. So that means we're going to have negative 2 times, instead of x plus h, we're going to have x minus h in here now. And this is still being squared, plus 5 times x minus h. And going through this, well, once again, we have to expand and we have to distribute, right? So expanding the x minus h piece, that's going to be negative 2. Again, feel free to FOIL it if necessary, but hopefully you guys can remember the blueprint of a minus b squared, and you just replace a and b with x and h, right? Those are the variables that we're dealing with here. So we have x squared, and then we're going to have minus 2xh plus h squared. And over here, we can go ahead and distribute the 5 like we did before. So we're going to have plus 5x minus 5h, right? So really the only key differences here are that, notice, this is now negative, where it used to be positive in the previous example, and this is negative, whereas it was positive before. But otherwise, same exact idea, right? You're plugging in something for your input and you're getting something out of it, and we just have to expand it just to make some sense of it. So now we're going to distribute the negative 2 to each piece. So that means we have negative 2x squared plus 4xh, right? Negative and a negative. So that means they turn into a positive when multiplied. So plus 4xh minus 2h squared. And over here, we have plus 5x minus 5h. And once again, there's nothing that we can condense. Everything is in terms of different variables. So we have to leave it as this. But our final answer is, and I'm just going to put a line here because that was a different question. Our final answer is negative 2x squared plus 4xh minus 2h squared plus 5x minus 5h. Okay, and again, notice the differences between everything. Our differences are that this was a flipped sign and that also this was a flipped sign. But otherwise, our inputs were relatively similar, right? The only difference was the minus versus the plus. So we should expect to get similar answers, just certain things will have flipped signs. Okay, so hopefully you guys got that and that wasn't too bad on you. Okay, let's go ahead and clear this and move on. So let's talk about the domain of functions. So the domain of functions is going to follow the same principles of the domain of equations, right? And when we're talking about domain of equations, we had two rules in particular. The first rule is that the denominator, so denominator of a fraction cannot be 0, right? We can't divide by 0. If you have a variable in the denominator of a fraction, then by default, you have to find where it's 0 because you can't allow the domain to include that number. Because if you include that number, then you have a problem, right? Then you're dividing by 0 at that particular number and the world blows up, right? You can't divide by 0. So that's our first one. And that's, again, the same rule that we talked about before in regards to equations. And the same other rule for equations follows here as well, right? The value underneath are in even powered root. So value under, and I'm just going to say this. Hopefully you guys understand that means even. Any number times 2 makes it even, right? So anything times an even, anything under an even powered root cannot be negative, right? So cannot be less than 0. If it's less than 0, that means it's negative, right? So what I'm talking about is this piece right here, the value that's underneath of a square root. We already talked about this, right? If you have a negative underneath of a square root, a 4th root, a 6th root, whatever the case, as long as it's an even root, if it's negative, you get a complex number, which means it's not defined by real numbers, right? We, again, always talk about the base case, the square root of -1. Well, square root of -1, we talked about that means I, right? Which means that there's no real answers. So, no solutions, right? Okay, so those are the two constraints that we have for domain for equations. And again, as it turns out, this is, in fact, the same constraints that we have for domain of a function. So let's look at an example for finding the domain of a function, but realistically, it's going to be the exact same thing as what you were doing before with domain of equations. Now, I will warn you, this is your second classwork assignment. I'll warn you, this is going to be a little bit longer of a domain question, a little bit harder than we're used to, but it still falls within the grand scheme of everything that we've been talking about before, okay? So give this second classwork assignment a shot. Again, you're trying to just find the domain of a function here. So let's see what you guys come up with. And the function is as follows. We're talking about f of x is equal to the square root of x squared minus x minus 6. Okay, so once again, we're trying to find the domain of this. Give it a shot. Okay, so yeah, this was probably a little bit longer. You had to work a little bit more for this one, but still not terrible as long as you just remembered what the goal is here. Okay, so the goal is it can't be less than 0, right? We can't have this piece underneath the square root less than 0, because if it turns out to be less than 0, then we have a negative number underneath the square root. And if we have a negative number underneath the square root, that means that it's not inside the domain, right? There's no solutions. There's no real numbers that would make that happen. So what we have to do is, okay, we set everything that's underneath our square root to be greater than or equal to 0. And the reason that it could equal 0 is because the square root of 0 is defined, right? The square root of 0 is still just 0. That's totally okay. So we can have 0 and we can have any positive number. We just can't have any negative numbers. So we set, okay, x squared minus x minus 6 is greater than or equal to 0. Okay, well, this is just a regular inequality question with variables, and we should know how to solve this, right? The way that we solve this is actually with test points. But before we can get to test points, we know that we have to factor this, right? So to factor this, we look at -6, and hopefully we can all do this by now. We see, okay, the factors are going to be -3 and +2, right? -3 and +2 because they multiply to give you a -6 and add together to give you a -1, right? Your B term. So we have x minus 3 and x plus 2 is greater than or equal to 0. So what we do is, well, the same standard procedure as what we learned before. We set these each equal to 0. So x minus 3 is equal to 0, x plus 2 is equal to 0. We see when we actually get 0, right? So we get 0 at x is equal to 3, and we get 0 at x is equal to 2, which means when we come down here, when we plot, okay, we're going to have, sorry, I just realized I didn't mean to put the dot immediately. So right here at -2, and also at 3, right? And the reason that I erased it is because I just wanted to talk about this again. Notice that we are including when it's equal to 0, right? It's greater than or equal to 0. So we're going to use closed dots, right? It's the inequality is 0 at these 2 points, 3 and -2. So we want to include when it's 0 because that's what the inequality is saying. So now what we have to do is we just have to test these 3 intervals, 1, 2, and 3, right? And we test them with test points. So we pick test points to match each of the intervals and see whether it's positive or negative. And what do we care about? Well, we care about when it's positive, right? Again, we set up the inequality such that we're looking for positive numbers only. If we're looking for negative numbers, then this fails, right? So we're looking to see when this expression is positive, so that way it's inside of our domain. So the points that I'm going to pick, again, you can feel free to pick any points as long as they're inside the intervals. I'm going to pick 0, I'm going to pick 4, and I'm going to pick -3. You can feel free to pick any other points. They'll all work the same as long as you do your math correctly. So let's go ahead and test. And I'm going to test -3. And that means I'm just going to be plugging them in right into what I factored, right? So plugging -3 in. So we're going to have -3 minus 3. -3 plus 2, right? And let's see what ends up happening. So that's what we had here, x minus 3 and x plus 2. So we're going to have -3 minus 3, which gives us a negative number. -3 plus 2 is also a negative number. And we know that a negative times a negative gives us a positive. And a positive is, in fact, greater than or equal to 0, right? So that one works. So we know that this interval right here, this whole interval up until we hit -2, that gives us positive, so that's great. Okay, we test the middle. So testing the middle, we're testing 0. We're going to have 0 minus 3 times 0 plus 2. Well, 0 minus 3 is a negative number. 0 plus 2 is a positive number. And we know that a negative times a positive is negative. Is a negative greater than or equal to 0? No, right? We don't want negative numbers. We only want positive numbers. So that's not going to work. And last but not least, we have to test 4. So testing 4, we have 4 minus 3 times 4 plus 2. This is going to give us a positive times a positive. And a positive times a positive is, in fact, again, positive. And positive greater than 0, in fact, it is. So hooray, we now have our second interval for our domain. So all that works. We know that that was negative, so that we're excluding that. And our domain in interval notation, we're talking about all the numbers that we notice that we have two different intervals, right? So we're definitely going to need to have that union piece. So think about them as one interval at a time. So we're talking about here, and I'm going to mark it in red, this piece. This is all of the numbers from negative infinity all the way up until we hit -2. And notice we're including -2, right? Because we're including when the inequality hits 0. So we're talking about that piece right there. And again, we're including 2, so we use a bracket. And this inequality, which I'm going to mark in blue, we're talking about all the numbers from 3, including 3, because again, we're including when it's 0, and all the numbers that are bigger than 3, like 4, 5, 6, so on and so forth, right? So bracket for 3 all the way up until positive infinity, and all we have left to do is just union them together. So our final domain of this expression here, and I'm just going to put my final answer right next to it. So my domain is going to be from negative infinity to -2, including 2, unioned with, including 3, from 3 to infinity, and that's our answer. Okay, now again, you can verify this very easily. If you plug in any other number into here, well, see what happens, right? Any other number that's not in your interval. So we tested 0, right? You can plug in 1 and get the same idea, right? If we plugged in f of 1, let's see what happens. F of 1, well, f of 1 means we're going to take the square root of 1 squared minus 1 minus 6, right? So 1 squared minus 1 minus 6. This means we're going to get 1 minus 1 minus 6. 1 minus 1 is 0. Minus 6 gives us square root of -6. And notice we get a negative number. This is not allowed, right? And hence, this is not in our domain. So just again, a quick test to show that 1 doesn't work. And that's great for us because 1 is inside this interval right here, right? The one that we saw wasn't allowed. Okay, so hopefully that wasn't too bad, and it should be a good refresher for you guys as far as test points are concerned. I know that that was on the midterm, so hopefully we remember that. Okay, let's see. Give me 1 second, guys. I just want to see how long I've been going. Okay, let's just get to one more topic here, and then we'll call it. Actually, you know what, guys? I think that we're going to call it right here. Because 47 minutes, if I keep going, I'll probably be over an hour before this chapter is done. So we're going to call it, and then we'll pick back up with functions in our next lecture. And I will adjust the homework as necessary. Okay, so feel free to reach out to me if anything here didn't make sense, or if you would want some elaboration on anything. Try the homework, see what happens, and of course, we'll talk about this more on Monday. Okay, so have a good one, guys. I will talk to you later. All right.